We continue with a similar example. In the previous example, we had 1 over z minus 1 over z minus 1. Now we are going to consider very similar example, but now we change this 1 by 2. And we are going to find the Laurent series around 0 as well. So what we are doing now is very similar to above. We just replace this f of z by minus 1 over 2 minus z. In fact, we just have multiplied with minus 1 in the numerator and denominator. So what does this mean? Well, now we want something which is close to the limit of a geometric series, and I need in the denominator something which is 1 minus something. And what I'm doing then is just to divide by 2 in the numerator and denominator. Then I obtain this, minus 1/2 over 1 minus z over 2. So now by putting this in front of this fraction, I obtain minus 1/2 times 1 over 1 minus z over 2, which is the limit of a geometric series where this u is equal to z over 2. So now I can replace this by the sum of a geometric series where u is equal to z over 2. So I keep this factor and multiply with sigma z over 2 to the power of n. And as usually, n is going from 0 to infinity. When is this valid? Well, we know that this u should have absolute value less than 1. So the absolute value of z over 2 should be less than 1. Multiplying with 2 on both sides of this inequality, I obtain that the absolute value of z should be less than 2. So this series expansion is valid in the circle with center at 0 and radius equal to 2. We can this is a good answer to our question, but we can rewrite this Laurent series in order to identify the coefficients an and bn. And well, we see here I can multiply this minus 1/2 by all these terms inside the sigma symbol, and then I obtain this expression, and multiplying this 1/2 by 1 over 2 to the power of n, then I obtain minus 1 over 2 to the power of n plus 2. So this is just the coefficients, and they are the an coefficients, because we are going from n equal to 0 to infinity, and here we don't have any negative exponents of z. So what we have done now is just to find the Laurent series expansion inside this circle. In order to find the Laurent series expansion in the remaining part of the complex plane, we do as above. We start with the expression of f of z, which is equal to 1 over z minus 2, and divide by z in the numerator and denominator. And what do we get then? Well, we obtain 1 over z over 1 minus 2 over z. And now I'm close to observing that this is just the limit of a geometric series. If I just put this in front of the fraction 1 over z and multiply it with 1 over 1 minus 2 over z, then I see that this is just the limit of a geometric series where u is u, the symbol u I've used before, is 2 over z. So therefore this limit must be equal to this sum. And of course I must not forget to multiply with 1 over z, and multiplying 1 over z with each term inside this series, I obtain the following. And you know that we can replace this fraction by 2 over n over 2 to the power of n over z to the power of n. And then I obtain, by multiplying with z to the power of minus 1, which is this guy, then I obtain this infinite series. And I know that this u must have an absolute value less than 1. Therefore, the absolute value of 2 over z must be less than 1. And multiplying with z, absolute value of z, on both sides of this inequality, I obtain that z must be larger than 2. In the other Laurent expansion, I found the expression valid for z less than 2. So this is the remaining part of the complex plane. So now I've found both the Laurent expansions. So we have two expansions. The f of z could be written as this sum or this sum, valid in these two regions.